I will be talking about the Fisher-Rao Riemannian geometry of equivalent Gaussian measures on Hilbert space. And so this will be the generalization of the following geometrical structures for Gaussian measures in Rn, from Fisher-Rao metric and distance to the infinite dimensional setting of Gaussian measures and Gaussian processes. So first I will review very briefly the Fisher-Rao metric for the set of non-zero center Gaussian densities on Rn. So let's consider the set of SPD matrices of size n by n, and so we have a correspondence between the set of SPD matrices and the zero mean Gaussian densities on Rn. So this set is characterized by, so of course a Gaussian density on Rn is completely characterized by its covariance matrix sigma theta, and it's characterized by k parameters, so k is equal to n times n plus 1 over 2. And so this can be given like this set can be given the structure of a smooth manifold, and we can define something we call the Fisher information matrix. So it's given by this expression g ij theta over there. And it in the case of Gaussian, this can be computed explicitly, and it defines a Riemannian metric on S, so called Fisher-Rao metric, which is the official information metric. It's kind of a central object in information geometry. And as I said, in the Gaussian setting, we can have an explicit expression for this Fisher-Rao metric, and so it's given by the expression of g ij theta over there. So where as I recall, the sigma here is the covariance matrix. And since we have the correspondence between the set of Gaussian densities on Rn and the set of SPD matrices via the covariance matrices, so we have this correspond to something called the affine invariant Riemannian metric on the set of SPD matrix, and so it's given by, so we have a closed form formula for the metric. That's a definition on the. Do we have like a pointer somewhere? Never mind. And so we have this. This is a point. Oh, thank you. Where's the pointer? How do we? Okay, this one. No. How do I point it? Isn't it the? Very famous. Okay, thank you. Thank you. And so we have this expression here for the affine invariant Riemannian metric on the set of SPD matrix. This is a very well-known formula, of course. And so now, just very briefly, we have the explicit expression for the affine invariant metric, and we have many things here are well known. As you know, in the previous talk, you actually saw it. So we have a unique geodesic joining any two matrices A and B has a closed form formula given by this expression here, and we have a closed form expression for the Riemannian distance as well. So there's a lot of mathematical structures, and of course this corresponds to the Fisher-Rao distance between the zero mean Gaussian densities on Rn. Of course, we have for the Fisher-Rao distance we did like a factor 1/2 over here. But basically, there's a one-to-one correspondence. So now, before I move to the set of the formula for the Fisher-Rao metric for Gaussian measures on Hilbert space, I would like to talk about the generalization of the affine invariant Riemannian metric to the infinite dimensional setting. Now, if we look at these formulas here, in the infinite dimensional setting, if we have A and B are covariance operators, for example, they are compact operators, and so these expressions are not well defined because if we have the A inverse would be unbounded because it's a compact operator, and then the log would not be will also be unbounded. So this expression would all blow up in the infinite dimensional setting. So to generalize it, this is the work of Logarithmic in 2007. So introduce a set of something we call the extended or unitized Hilbert-Schmidt operator. So instead of just the Hilbert-Schmidt operator, we are considered the set of A plus gamma I, where A is Hilbert-Schmidt and which I is the identity operator. And so this is a space under the extended Hilbert-Schmidt in a product and norm. So we have this expression here for the so it's defined so that the identity operator, the scalar operators and the Hilbert-Schmidt operators are orthogonal to each other. And we have this is the extended Hilbert-Schmidt norm. And it's defined so that for the identity operator, the extended Hilbert-Schmidt norm is the identity operator is equal to 1. Whereas with the standard Hilbert-Schmidt norm, the identity operator would have norm equal to infinity. And so we can consider the set of positive definite unitized Hilbert-Schmidt operators. And so the set here of the form A plus gamma I here with the 0. And so this is a Hilbert manifold, and it can be we can define like the affine, the generalization of the affine invariant Riemannian metric. And so yeah, everything is the same except that we just have like the A plus gamma I greater than 0 instead of just A. And so this is also, so everything generalizes. This is geodesic complete, non-positive because it's like a Cartan-Hanemann manifold, and we have a unique geodesic joining every pair. So over to A plus gamma and B plus mu I, we have the same expression, and we have the same expression for the Riemannian distance as well. So this is I will discuss later on that this actually can be considered as a kind of a regularized version of the Fisher-Rao distance between equivalent Gaussian measures on a Hilbert space. Okay, I'm going to actually skip this. So now, of course, let's talk about the Fisher-Rao metric for Gaussian measures on an infinite dimensional Hilbert space. Now, when we have a Hilbert space which is infinite dimensional, we have no Lebesgue measure, so we cannot really talk about the density functions, just like Gaussian densities. But we can consider the set of probability measures equivalent to a fixed measure mu0, so that we can compute the Radon-Nikodym densities, and then with respect to this mu0. And so, if we just focus on this particular set, then we can have the then we can generalize the Fisher-Rao metric. So just one particular set, of course. So there's so of course the most work in information geometry has been the finite dimensional setting, but we have a lot of also recent work on the infinite dimensional setting. So we have work of Piston and his collaborators. We have Sampi and Chivilesco and Rogatin, Chena, and Piston. So we had the work with the highly abstract setting infinite dimensional binary manifold models on all X spaces. Probability measures equivalent to a given one. We have the work of Newton. We consider Hilbert manifold probability measures of finite entropy. And with the Fisher-Rao metric, the setting is general Riemannian metric, and we have the series of work by Ye, Yost, Ley, and Schwarzhofer, where it's considered like a set of, they utilize the natural motion of the set of probability measures into binary space of all finite sign measure under the total variation norm. So these works are highly general, and they have a highly general setting and very highly abstract. So what I'm going to talk about is just a very specific, a very concrete setting, the set of center Gaussian measures, which are equivalent to a given one. So now in the on Hilbert space, the situation is very different from Rn. In Rn, any two Gaussian densities are equivalent because they have the same support. In an infinite dimensional Hilbert space, the situation is drastically different. We have the classical theorem of Feldman and Hartree. So we have two Gaussian measures that are either mutually singular or equivalent, so they have the same support, or they have the supports are disjoint. And we have and that is necessary and sufficient conditions for the equivalence of two Gaussian measures on Hilbert space. So it's actually it's fully characterized a long time ago, at least in the 1970s, I think. So we have the two Gaussian measures are equivalent if we have the following. We have so the difference between the mean is has to be in the range of, for example, the skew a half here, and we have and the covariance operator has to be related in this form, in this particular formula here, where S here is a Salvatore Hilbert-Schmidt operator, so that I minus S is greater than 0. So now if we fix an operator, so let's not just consider the center setting. So we consider a fixed Salvatore chess class operator C0, and we have, so that we can consider the set of Gaussian. So we consider the set of Gaussian measures equivalent to equivalent to mu0, and so we can consider this set of all Salvatore operators, Salvatore Hilbert-Schmidt operators, so that I minus S is greater than 0, and we can consider the set of corresponding covariance operators. So we have the set of corresponding Gaussian measures. So these are all equivalent to mu0, and it can be considered as parameterized by S in this set here for I minus S greater than 0. So we have the parameter instead of this theta in the Euclidean setting. We have this set of Salvatore operator S here, Hilbert-Schmidt operator S here, and so this is the Hilbert manifold. It's an open set. It's an open set and the set of Salvatore Hilbert-Schmidt operator, and so we have the set of measures which are parameterized by a Hilbert manifold. And also this set can be the corresponding set of trace class operator of the corresponding covariance operators can be also considered as a subset in a Hilbert space. So it's a Hilbert manifold, and it has its we can characterize its tangent space and so on. And so, what is the definition of the generalization of the Fisher-Rao metric or the Fisher metric here? So now, instead of before we're computing like the derivative dt theta of the log of p theta with the p theta being the density, now we compute the logarithmic derivative, so the kind of derivative of the Fisher derivative of the Rao-Riemannian density, and then on the tangent space. So v1 and v2 here are two vectors on the tangent space at any particular point s, and so this would be the expression for the Fisher-Rao metric. And so of course now we have to compute this logarithmic density. So we have to compute the Rao-Riemannian density of d mu and mu 0. So to compute to express the Rao-Riemannian density of the two equivalent Gaussian measures, we need something we call, well, at least this is one way to do it. It's something called via something called the white noise mapping. So this is a mapping from H into L2 H from L2 into mapping W from H to L to H mu, where in the case when so it's defined so that on the set like Q half H here is given by an explicit formula, and then in general we can, so it's actually this is an isometry, and then in general we can define for any Z belong to H via a limiting process. And so this is also the white noise mapping, and so we can actually express we have explicit expression for the Rao-Riemannian density using any two Gaussian measures, equivalent Gaussian measures, nu and mu via this white noise mapping here, where the alpha k and the phi k are the eigenvalues of the operator S. And so it has a closed form formula. It's rather complicated, but that's a closed form formula. And in particular, in the case when S is trace class, then we can actually express it more explicitly in terms of S. So I just want to point out that this Q or half Q negative or half Q is, of course, if we just write directly, then it's not well defined because Q is compact. So the Q negative or half is actually unbounded. So this is not like a direct expression, but it's actually expression in terms of a limiting process. So we define an expression using a projection operator on finite dimensional space, and we take the limit in L2. So this is an expression defined by a limiting process. And so now we can compute the logarithmic derivative. So it has an expression in the case when both S and V are trace class, so we can actually write this expression here. And again, this expression is a limiting process. This is a limiting process when we have to compute with a finite dimensional projection operator first, and then we take the limit in L2. And so we can first, so we have an explicit expression for the case S and V are both trace class, and then we can take the limit in L2 in the case when S is Hilbert-Schmidt and V is trace class, and then S is Hilbert-Schmidt and V is Hilbert-Schmidt, so we take the limit. And so we can compute the logarithmic derivative. So the log of the Rao-Riemannian density is Fisher differentiable. And so, of course, the thing that we care about is just the inner product here, and it's given by this expression here. So this gives us the Fisher metric. So this gives us the Fisher metric on this set of equivalent Gaussian measures equivalent to mu 0, and the corresponding Riemannian metric on the set of covariance operators is given by this expression. So it has the same expression as in the finite dimensional setting, except we have to write it in this form. We cannot. So in the finite dimensional setting, we can also write it like sigma negative 1 a sigma negative 1. A, but it has to be written in this form because otherwise it can be unbounded. So equivalently, we can also compute it via the compact Leibler divergence. We can take the second derivative of the compact Leibler divergence, and we have the closed form expression for the compact Leibler divergence between two equivalent Gaussian measures on Hilbert space. So if they are mutually singular, then it's infinite. If they are equivalent, then they have a closed form formula. So if we take the second derivative of this expression, then we also obtain the same thing. We also obtain the expression for the Fisher-Rao metric. And I just want to mention that on the set of equivalent Gaussian, the set of the corresponding covariance operators, this is generalization of the set of SPD matrices corresponding to the Gaussian density. We can compute everything explicitly, and they have the same expression as in the finite dimensional setting. So we can compute the Levi-Chitac condition, we can compute the Riemannian curvature tensor, and the Schönfeld curvature, and so on, and everything. And it's also the same, like it's non-positive. And we have this kind of the also closed form expression for the geodesic connecting it to any two pair of covariance operators, and we have the Riemannian distance as well. So of course, this expression is only defined in this particular setting, but as I said, in general, it's not defined. It's only defined in the setting when they are related by this particular form. And so they are related. So this is related to the Riemannian distance between positive definite Hilbert-Schmidt operators, because we can show that if we have these two operators, a plus gamma I and b plus gamma I here, and we take the kind of the phi invariant Riemannian distance between them, then they would. Then when the regularization parameter goes to 0, we obtain besides this expression, which is the kind of twice the Fisher-Rao distance between the two equivalent Gaussian measures. So the so before, people were actually studying the Riemannian geometry of positive definite operators, Hilbert-Schmidt operators, purely from a mathematical viewpoint, because they wanted to have a Riemannian manifold of which generalizes the phi invariant Riemannian metric. But we can show that the distance is actually really can be considered as a regularized version of the Fisher-Rao distance between two equivalent Gaussian measures. So it's like kind of a very interesting connection between the two settings, purely differential geometry and statistics. Now, okay, I'm running out of time, so I really have much time to talk about this. But we can also show that in the phi invariant Riemannian distance, we have the convergence between two operators we have the convergence in the phi invariant distance if the operators converges to the Hilbert-Schmidt norm. So this actually can be useful if we want to compute like the sample complexity. Okay, so I only have a few minutes left. I just want to say that previously we have the expression for the in the abstract Hilbert Gaussian measures on Hilbert space setting. We can actually obtain the closed form formula. We can obtain finite dimensional estimation in the case of Gaussian measures corresponding to Gaussian processes. So if you have like two like a Gaussian processes, for example, on an interval, a compact interval T, and we have the correspondence. There's a one-to-one correspondence between measurable Gaussian process and Gaussian measures. So which this is the mean function M and covariance function K. So then the corresponding covariance operators are given by the integral operator with kernel function with covariance function KST. And so we can come. This is like an example of the two Gaussian processes. Two Gaussian processes kind of generated by these two covariance function, and we can compute we can estimate the distance between the corresponding to covariance between the corresponding Gaussian measures. So this actually has been kind of considered a lot in the setting of functional data analysis, where we consider Hilbert-Schmidt distance, and also recently in functional Bayesian neural networks, where we consider the Wasserstein distance and the K-Young divergence. So I just want to show that in the because here we have the distance between two infinite dimensional Gaussian measures, and we can actually show that we can estimate them by the distance between finite dimensional Gaussian measures here, where we sample m points from the interval of t from 0 with the interval t m points, and we have the corresponding Gram matrices, and we can estimate this. Now this is the distance in L2 t nu with h is L2 t nu. This is in Rm. So this Rm is not exactly a subspace of L2. So what we have to so intuitively, they should be this one should be the finite dimension estimation of this. But to do it properly, we actually use the methodology of reducing kernel Hilbert space. So okay, just via the something we call the cross covariance operators. I will not have time to go through this. I'm going to show that we can obtain the this is the estimation of the infinite dimension distance, but the finite dimensional distance, and we have the kind of dimension independent sample complexity. And so where kappa here is just the size of the kernel. So This is and this sample dimension independent sample complexity is due to the Hilbert-Schmidt convergence that I was talking about just now. Just give you an just to show you that this is the kind of the blue thing here is this is the kind of the distance between the estimation of the distance between these two the Gaussian measures corresponding to the Gaussian processes, and this here the two Gaussian processes are much closer to the distance is a lot smaller. That's okay. So summary, so I was talking about the generalization of the Fisher-Rao metric and distance between Gaussian density from Rn to the infinite dimensional Hilbert space settings. Of course, we're talking about only in the case when we have equivalent Gaussian measures on Hilbert space, and we can show that we have a connection between the affine invariant Riemannian distance between positive definite Hilbert-Schmidt operators, which can be viewed as a regularized version of the Fisher-Rao distance between the equivalent Gaussian measures, and we have Hilbert-Schmidt convergence relates to the dimension independent sample complexities, and similar results actually hold for the setting of the entropic regularization of the two versus sign distance. So a lot more theoretical results can be obtained. Of course, we have to work on the numerical and practical work with Gaussian process, and of course we have to move beyond the Gaussian process setting. Thank you for your listening, and I will be happy to take questions, comments, suggestions, criticisms. Thank you very much.
So, any questions or criticisms?
Thank you very much for this talk. I don't have a criticism at all, actually. I'm very glad to see a bit of probability inside this framework. The story is actually I have the same result as La Rotonda in my thesis.
Right.
And it's a funny story because when I was submitted my thesis and Tudor Ratio was one of the referee,
right.
He told me, hey, there is this guy from Argentina who have the same theorem as you. So I was completely upset. Why this guy at the end of the world had the same theorem as me at the same time? So of course,
La Rotonda, Gabriel La Rotonda.
No, the story is actually So then I met Gabriel La Rotonda, and actually I will meet him in 1 month in Buenos Aires.
Okay.
So you can come along and try to work with him also. The funny story also, he was quicker than me to publish his results.
Oh.
Yes. It was in my PhD, so I just left it there for 20 years. But then I said, the same result, but we have different way to prove it.
Right.
So it's about this geometry on the SPD in infinite dimensions.
Right.
So now I submitted this year, and now it's published. And the main center point of this is called Mosto decomposition theorem,
right.
Which I hope will have a lot of application. So I'm very glad if people from probability look at this theorem. So Gabriel and I have the same theorem. This is the Mosto decomposition theorem in infinite dimension.
Right.
Which is a generalization of polar decomposition.
Right.
So it gives you more decomposition blocks. Please use the theorem. It's a beautiful theorem in geometry. So
Oh, thank you very much. Thank you very much. I would love to discuss with you further. Thank you very much.
Any more questions? No, I think we should move on then. Thanks again.
Thank you very much.